this webinar, which will be probably a relatively hot topic and relatively technical webinar, but at the same time, very core to our activity and especially more over to our methodologies. Of course, there are probably no much need to introduce for many of you Arthur Charpentier, who most of you know very well. However, for those who don't know him yet, let me summarize his impressive CV. Arthur is full professor at the University of Montreal, in charge of actuarial sciences in Canada. Therefore, he is also professor at the University of Rennes in France. He's member of different editorial boards of the Journal of Risk and Insurance, a well-known journal. Even Denis Kessler published it in his journal, and as well as George John, Pierre-André Chiappori, who are the pillars of the foundation. He is also a member of the editorial board of the Aston Bulletin and Risks. He did a few years ago computational actuarial science with R, and more recently wrote Insurance, Bias, Discrimination and Fairness, whose references can be found on the foundation website, and which I would, in any case, recommend to any up-to-date actuary. He is also the former director of the Data Science for Actuaries program of the French Institute of Actuaries. The recent work of Arthur focuses on climate change and predictive modeling insurance, more specifically in the context of fairness and discrimination. He leads the SCOR Share program on fairness of predictive models and application to insurance markets. Some of you may have attended the recent stimulating and fascinating seminar he organized at SCOR on the topic. Today, Arthur will share with us its views on the relationship between econometrics and machine learning, a very hot topic for actuaries and statisticians and economists also as well. He will present a rather technical and rigorous thoughts. This is a topic of prime importance for our actuaries and underwriters, as it revolves around the implications of machine learning for our contract design and pricing work, and more generally for our risk assessment. I would not like to prolong this introduction unnecessarily, as I must hand over to Arthur, who will explain much more brilliantly and rigorously and technically what I will attempt to explain to you rather clumsily. Dear Arthur, thank you so much to have accepted to make this key presentation. You have now the floor for 45 to 60 minutes, roughly speaking. Your presentation will be followed by a Q&A session of maximum 30 minutes. And for the audience, please keep your questions for the Q&A session, except for pure comprehension questions. Thank you so much, and you have the floor, Arthur.
Thank you so much, Philippe. So I'm going to start sharing my slides. So it should be okay, right?
Yes,
perfect. Thanks. So yes, my talk will be on econometrics and machine learning. Thanks, Philippe, again for the introduction. You said that I'm going to be rigorous, but actually I'm going to be a little bit vague on some concepts like econometrics. Econometrics usually is designed for economists, so obviously there will be connections to economics and economic theory, but also econometrics is what actuaries are using. They use econometric models for a lot of things, for reserving, but also pricing. So I'm not going to get too much into the details, but I'm going to try to explain what could be the difference and the connections between the two. So first, I should mention that it will not be econometrics and artificial intelligence. It was mentioned in the email, but I will just focus on machine learning and to be a little bit more specific about the classical supervised machine learning when we try to predict a variable of interest. It's based on some joint work with colleagues, students, former students. I mentioned Antoine Lee. So Antoine is working at SCOR. He used to be a PhD student of mine, and we wrote a paper which was entitled Econometrics and Machine Learning. So I'm going also to make some connection at the very end of the talk with the topics mentioned already by Philippe, which is what we're working on in this project, which is about fairness and more specifically, we'll talk about calibration because it's something extremely important in natural science, and it's a good way to understand differences between econometrics and machine learning. So obviously, econometrics and machine learning, they're the continuum between them. It's obviously not completely black and white or blue and red. 10 years ago in that paper I rewrote with Antoine, we said something like econometrics and machine learning have a common goal. It's to get a prediction for a variable of interest using explanatory variables. So obviously they focus on the same thing, but there will be differences. And to stress the differences, I'm going to be a little bit simplistic in some cases. So I'm going to emphasize the differences to explain why we have different cultures. I'm going to get back on this point of different cultures between the two communities and try to make and to connect them with different bridges to see how we can go from one to the other, which is extremely important. Long story short, between econometrics and machine learning, there will be computational statistics, statistical learning, and those correspond to computational techniques where we have actually mathematical probabilistic guarantees, which is something that could be extremely important in terms of risk, actually. So to start with some general motivation and some concepts, I'm going to start with a very famous article that Leo Breman wrote 25 years ago about this idea of having two cultures that I will call econometrics and machine learning. So he mentioned that there are two cultures in the use of statistical modeling to reach conclusion from data, meaning we want to make a prediction. One assumes that the data are generated by a given stochastic data model, which is what I call econometrics, because actually when you do econometrics, basically you use economic models. Okay, so we have a model, we have economic theory, and we want to use that theory to make some predictions, something like that. So this will be the first culture. And the second one is the other that uses algorithmic models and treat the data mechanism as unknown, which is basically what I will call machine learning, actually. Okay, so this is more or less the difference that I have. So I'm not the only one. Leo Breman mentioned this differences between the two. It was also mentioned in a blog post by Tyler Cowen, who was quoting Susan Atsey, saying something like the foundation of supervised machine learning method is that model selection, like cross-validation, is carried out to optimize goodness of fit on a test sample. So it's really about goodness of fit. It's about prediction. Okay, so I will get back on this point of cross-validation because it is something that is also very important to understand the difference between machine learning and econometrics. Cross-validation has to do with running scenarios and see the differences on predictions. So we will not have what we used to have in econometrics, which is more penalization and validation criteria. And as he said at the end of the post, a model is good if and only if it predicts well. So that's basically also the difference between machine learning and econometrics. In machine learning, we really care only about predictions, and we want predictions to be good, whatever. So, okay, so we can moderate that statement because we start to have questions about interpretability, understanding what the model is doing, explainability, and this kind of stuff. But initially, there was a clear separation between econometrics and machine learning. Also, if we get back in time, and I'm going to get back in time because it's important to understand how econometrics was founded. Econometrics was founded related to these SCOR Foundation commissions in the US. And when you start looking at the papers in the 40s, there was this probabilistic framework. It was mentioned in this paper by William Tomek. Charles Munsky mentioned that in another paper, saying that in the paper by Trygve Alvelmo in 1944, building the econometric society, actually, all of them mentioned the probabilistic structure. And this is something extremely important, which is the fact that econometrics is built on probabilistic foundations with probabilistic models. And this is something that is going to be extremely important in economics, because that will give us like confidence intervals that we will not have with machine learning. And I would say that as actuaries, we like having this probabilistic framework, because when you want to talk about risks, you need a probabilistic framework. So I think this is something that you should keep in mind to understand the differences between econometrics and machine learning. Okay, so this is my starting point. So econometrics and machine learning. So econometrics is going to start with this idea of having probabilistic models. Okay, so again, if you get back to this Avelmo's papers in 1944, tools developed by econometricians will be based on statistical theory, meaning statistical mathematics. So there will be a lot of mathematical properties. I'm going to show you a lot of math in the slides, mainly to emphasize the fact that actually econometrics has to do with mathematics. We go through computations and calculations, while when we do machine learning, it's just running algorithm without any guarantees, actually. This will be more or less the difference. So econometrics has to do with a probabilistic framework. It's about assuming a data generating process with explicit stochastic components. We're going to focus on inference, which is estimate parameters, stating a hypothesis, and also, but I won't mention it today because actually I gave already a talk yesterday at the French Institute of Actuaries on causality, but econometrics is well designed for causal inference, which will not be the case for machine learning, actually. Okay, so this is more or less the idea of econometrics. On the other hand, we have machine learning. Okay, so it's on the right side of my scope, machine learning. So I start with a very old statement, actually, from Arthur Samuel in this end of the 50s. It was actually in an article about using machine learning to play games, right? And it says something like machine learning is the field of study that gives computer the ability to learn without explicitly being programmed. So it's really the fact that we're going to give the targets to the machine and ask the model to be as precise as possible. So there will be no structure. We are not going to explain what we try to model, but we want to get the best prediction as possible. Okay, so that's exactly what we will be using. And I think machine learning didn't change too much if we compare that to this statement. We can also find that in a more recent paper, which is about the taxonomy of loss functions in machine learning, which is the fact that in machine learning, problems are cast in the form of loss function. Okay, so you want to minimize what we call a loss, which is basically a distance between what we observe as a y and what we predict that we will call a y hat in statistics. So it's the difference between what we observe and what we predict. We want to be as small as possible. Okay, so the model will be optimal when this quantity is minimized. That's basically everything you need to understand about machine learning. And in a more recent paper on deep learning by Jan Gonfello, Joshua Bengio, and Aaron Corville in Montreal, they have this statement saying that machine learning is essentially a form of applied statistics. So again, I want to stress on the words, but econometrics has to do with theoretical statistics, and machine learning has to do with applied statistics. Right, so it's about emphasizing the fact that the use of computer is important to statistically estimate complicated functions. So what we call a function will be a model, actually, and we have a decreased emphasis on providing confidence interval around those functions. Okay, so if you care about confidence intervals, obviously you were trained as an econometrician and you have this culture of econometrics. But if you don't care, and if you really care about predictions, this is machine learning, actually. Right, so we have the second culture. Okay, so it's really about focusing on predictive accuracy. Okay, so machine learning has to do with giving good predictors at any cost somehow. Okay, we really want to get a good model. I will talk a little bit about generalization, actually, because it's not getting a good accuracy on observed data, but it will be to get a good accuracy on new data, which is something slightly different and gives a lot of interesting tools, actually, that could be used by econometricians. Machine learning has a lot to do with optimization. Okay, so it's finding the best function, the best model, the best whatever. So it's really about optimization. I have to stress, and I will get back on this idea in a second, but it's also the case in statistics. Okay, so if I talk about maximum likelihood, it's also an optimization problem. Okay, but it's an optimization based on probabilities, which is slightly different. But it's optimization based. We just want to minimize a loss function. The focus will be on accuracy and generalization. So again, it's not to focus on the data we have, but new data we could have. And somehow we start to have this idea of focusing a little bit on interpretability, which was completely out of the problem when people were using machine learning, actually. Okay, so we're going to get back to this these two cultures, right? So I'm going to discuss machine learning and econometrics. I will start talking about OLS. Okay, I think a lot of problems are coming from the fact that ordinary least square, it's seen as an econometric problem, but actually, when you talk about ordinary least square, actually this is a machine learning approach. So there's a lot of confusion the way we teach econometrics, because we start teaching econometrics as a machine learning problem. Usually we don't put any probabilistic background, any probabilistic framework. We start by minimizing the sum of the squares of the residuals, which is exactly what we do in machine learning. But then we somehow get back to probabilistic models, but I think it's not a good way to explain the differences. So I'm going here to make connections between machine learning and econometrics through ordinary least squares. And then I'm going to talk about classifiers, because I think it's important for actuaries, because we don't see a lot of regression problems in natural science. We see more classification problems. And also because in machine learning, they've been focusing a lot on classification. So classification in ways when you have a y variable of interest, which is categorical, usually 0 and 1. My point in this section will be to explain that if you've been studying econometrics, you know that you should go for logistic regression. The first instinct of econometrician is to go for logistic regression when you have a classification problem. But actually, interestingly, there's a lot of way to look at this problem, and all the different techniques give you something very close to the logistic regression. So you end up with the same kind of model with different paths, which is something I think very cool, which makes a lot of connections between econometrics and machine learning. With different approaches, with different techniques, we're going to end up with the same kind of model, which is more like this logistic regression. Okay, or this logistic model. The way we get the parameters will be different, but the structure will be the same. And then I will talk, if I have some time, about generalization and cross validation, because it's a good way to understand the differences between the two. And then I will talk about calibration, just to highlight the fact that sometimes in econometrics and machine learning, we really don't care about the same things. Calibration is a good example, because it's an extremely important problem in econometrics and actual science, but absolutely not in machine learning. So using machine learning techniques, when you care about calibration of probabilistic scores, will lead you to very problematic issues. And we'll talk about that, right? So we started with this. So first, I'm going to talk about models, right? So I will have this linear models and classification, and then I will get back to those different concepts. So about the models. Ordinary square is how we start teaching econometrics. We have a series of points, so blue points, and we want to get a model. It has to be simple. Again, I'm going to get back on this idea of simplicity. Here it's supposed to be linear. And how do we estimate the unknown parameters, beta? Well, just by minimizing the sum of the squares of the residuals. Okay, so we're going to quantify the difference. So the difference between y hat and y will be my epsilon hat. Okay, so the residuals, what is not explained by the model, and the sum of the squares of those residuals should be as small as possible. There's no probabilistic model here. Okay, so I'm just starting as a machine learning. So I put it in red just to highlight the fact that when you talk about OLS, actually you talk about machine learning. Okay, so ordinary least square, you have a problem like that one. So you assume that you're going to get a linear function, and it's just an optimization problem. Okay, so ordinary least square means minimizing the sum of the squares of the residuals. Okay, and you're glad because, well, you have a quadratic function, so you can explicitly get the formula. So that will be also one difference between machine learning and econometrics, at least at the beginning, which is in econometrics, we like to get explicit formulas. In machine learning, you don't care. But this statement is way too simple because, as we will see, once we leave the regression, we don't have any explicit formulas, actually. Okay, so it's only for this very simple case when we have a regression, when we want to minimize the sum of the square of the residual when y is continuous, that we have this explicit formula. Okay, so it basically is just using linear algebra because we have this linear structure in the model. So we end up with a prediction. We're glad because we also have a geometric interpretation, right? We have projections. Okay, so that's really cool because we can visualize things. But again, there's no probability here. Okay, so I think it is really a machine learning problem. Okay, so we have this technique mainly coming from machine learning, which is we're going to minimize the sum of the square of the residual, which will be my loss. Okay, I end up with an explicit formula, but that will not be the case for classification. And actually, if you want to do something more, you need more assumptions. This is where we have econometrics. Econometrics has to do about the fact that we add some assumptions. We're going to assume that we got Gaussian residuals, or we're going to assume that the distribution of y conditional on the covariates will be Gaussian. And in that case, we do what all statisticians are trained to do, which is we're going to use maximum likelihood. Okay, so we're going to maximize the likelihood of my data, and surprisingly or not, we end up with the same output. The beta will be exactly the same, just because, well, when you compute the maximum likelihood, you end up with minimizing the sum of the square of the residuals. So interestingly, we get, as we will always have, a common output will be the same, but coming from different models. One is coming from this idea of minimizing a loss. The other one is try to estimate some parametric probabilistic model. So we end up with the same model, except that now we have this probabilistic framework that could be extremely interesting because we can derive a lot of things. It's possible to do some inference, to quantify uncertainty. It's possible to prove that the estimator is unbiased. We can prove that we have a minimum variance. So all those properties are extremely interesting because, well, we can say something about the power of this estimator. We know how good it is. We can get confidence interval. And because of the properties of the Gaussian distribution, not only we have properties on the of the parameter, but also on predictions, which is usually what we care about. Okay, we're going to get a prediction, which was possible with my machine learning approach. I've been able to get an estimation of the parameters, so I've been able to make predictions, but that's it. If you want something else, you need more. Okay, so you need to quantify uncertainty and you need additional assumptions. And then you can do the math because, well, the math is very simple. It's just linear algebra with Gaussian distributions. So this is what we do as econometricians. But it's not completely true. It's still possible to do something.
It's
possible to turn off the mic, please. Thank you. It's possible to get almost similar properties without doing any mathematical calculations or to have any explicit probabilistic assumptions. Okay, so what I did is I got my model, I made some probabilistic assumptions, I've been able to derive properties. But actually, we can start also from the machine learning approach, saying that we got some data generated somehow, and we want to quantify uncertainty. So there's something coming out from Bootstrap. So Bootstrap has solid statistical and probabilistic foundations, and it's possible to replicate this idea of getting uncertainty. And we can replicate that. So it's coming. So this is in between machine learning and econometrics is Bootstrap. It's the idea that we can mimic the sample by creating fake pseudo sample that look like the one we have in the data. So basically, it's just subsampling. Okay, and then we can get new predictions, new fits. Okay, so you create a fake data. You create you estimate your model on that fake data. You can get, as you can get on the left, the estimation of the intercept, or you can get an estimation of the slope, or you can get an estimation of the prediction of whatever data you have. Okay, so it's possible to get a distribution just by resampling a lot. And what you observe is basically you end up with something very similar to what we have with probabilistic models. Because in theory, with this Gaussian assumption, we got a Gaussian distribution of the beta hat, we got a distribution, a Gaussian distribution for the prediction, but actually, if you subsample, you get more or less the same kind of properties. So it's possible to get more or less the same kind of output, some quantification of uncertainty without making any assumption on the distribution. We just play with computers, basically. We just reran samples. Okay, so of course, this is valid because Bootstrap has solid probabilistic foundations, but it's still possible to avoid making explicit probabilistic assumptions and still get quantities that will give you insights about the uncertainty in your predictions, right? So this is also something you can do with linear models. Now I can move to classification. So classification has to do with the fact that Y is binary or categorical, but let's focus on binary, so 0, 1. So you want to see if someone is going to get surgery, if someone is going to get a claim, if someone is going to go to the doctor or whatever. So it will be 0 and 1. We have, again, the two different cultures, the probabilistic one, econometric modeling, which will be related to the modeling through a Bernoulli variable and not a Gaussian distribution. There is another one, actually, which was initiated by Fisher, which is the discriminant analysis. So you have a very weird way to get to this modeling, but actually you end up with something which looks like the logistic regression again. And then I'm going to show you two examples of techniques used in machine learning. And again, we will end up with a logistic regression somehow, right? So the idea of logistic regression is very simple. So as we did for the regression, where we assume that Y conditional on X should be Gaussian, we're going to assume that Y conditional on X will be Bernoulli distributed. And because we got this heterogeneity, the probability should be a function of the X, of the explanatory variables, and the function will be very simple. So it's just this exponential of linear combination over 1 plus the exponential of the same linear combination. It's coming from the model on the log of the odds. Okay, so you're going to assume that the log, of the odds ratio is going to be an exponential of a linear combination, and you end up with this explicit formula that you have on the right. Okay, the probability for an individual will be this exponential over 1 plus the exponential. Okay, so this is the logistic model, and the inference, well, because we have a distribution, we can do maximum likelihood. Okay, interestingly, there's no explicit formula. But there's a lot of things that we can say about this estimation. So first, this is how it looks. Okay, so I'm going to get here I got two explanatory variables, x1 and x2, x1 on the x-axis, x2 on the y-axis. And then I'm going to use colors to tell you what was the y. 0 will be red, 1 will be blue, and we want to estimate the probability to be 1. Or because of the Bernoulli property, probability to be 1, the expected value of y. Okay, which will be what we use as a premium in insurance. Okay, so we got this kind of function. Okay, so we got this surface that we have. Okay, this is a logistic function. So you can see that we have straight lines on the right because, well, logistic regression is a linear model. Okay, so when you look at the ISO probability curves, so giving you the same probability, you get straight lines. Okay, so we end up with this one. Okay, so this is more or less what we want to model. Okay. So we have this idea of using maximum likelihood. So I'm going to be a little bit fast on this one, but you write the likelihood. You end up with a very classical equation, which is the one that you have on the right, which is the transpose of x times the difference between what you observe, y, and what you predict, which is p hat, should be equal to 0. This is a very simple equation. Unfortunately, because we want to estimate not pi hat, but beta, this is nonlinear in beta because we have this transformation. Because we don't have a linear model, it's linear through this exponential over 1 plus the exponential. Because of this nonlinear function, we cannot solve it explicitly. So we're going to need a computer, actually. You cannot run a logistic regression without a computer. You need to solve it. Okay. So I'm going to talk a little bit about computations because it's also very important in econometrics, actually. The other point is, because we do the math, we can get explicit formulas. Like the first order condition, which is the fact that the derivative of because when you want to reach the maximum, the derivative should be equal to 0. You have this expression that you have when you look at the derivative with respect to the intercept, which is the property you have on the top right, which is what we call in economics or in actual science, a balance property. The first order condition, when you differentiate with respect to the intercept, tells you that the sum of what you observe, the sum of the y, should be equal to the sum of the predictions. The sum of the losses is equal to the sum of the premiums. This is extremely important because it's a balance property. You have guarantees above that. Okay, if you use a logistic regression on a portfolio to estimate probabilities to claim a loss, probability to die, and if you use this model to assess your premiums, then on average, your portfolio should be well balanced. This is an extremely important property that is inherent of the way we estimate parameters in the logistic regression through the maximum likelihood. As we will see, unfortunately, we don't have these kind of guarantees with machine learning. So it's kind of problematic, I think, for actuaries because we have no guarantees to have this balance property when you use a different model than the logistic regression. So I think actuaries love econometrics just because they have those guarantees that the model will satisfy some very specific properties that are desirable and have econometric interpretation. Okay, and this property, actually, I mentioned that because it's very related to this problem of calibration that I want to talk a little bit at the end if I have some time. Okay, so it's possible to derive a lot of things because of the maximum likelihood properties. It's possible to get Gaussian asymptotic normality. We can get confidence interval, all of these kind of things, but we don't have any explicit formula for beta hat. Okay, so at some point we need to make, we need a computer. Okay, so, but we don't need a computer to learn a model. We just need the computer to solve the optimization problem to get the beta, and then we're going to use the beta. So we just need it at one small point, which is to get a numerical value for the beta hat. Okay, so we're going to use the gradient descent. So gradient descent is very simple. You just have this function. And usually in econometrics, we usually have those sort of convex functions, like the minus the log likelihood. So you want to minimize this function. As you can see on the graph, there is a minimum. Okay, so you want to reach it. As I told you, there's no way you can get an explicit formula in the context of the logistic regression. So we're going to use an algorithm. Okay, so this is the one derived by Newton in thousands of years ago. Sorry, hundreds of years ago. Which is the fact that we want to find values where the gradient is equal to 0. So it's just finding zeros of a function. So this is what Newton was working on. So you start with a point, and then you're going to go down. Okay, so you go through your gradient, okay, at the speed which is given by the Asian matrix, and you're going to reach the optimal value. Okay, as you can see, it's going to be extremely fast. So it's a property we have with econometrics, actually, with GLMs. This optimization routine actually can be a little bit complicated in the case where you don't know the explicitly the gradient or the Asian. You need at each point to estimate those quantities. Okay, I want to go from a starting point down. We need to compute the Asian. We need to compute the gradient. The thing is with linear models, those are extremely simple. They're just linear functions. You just need some matrix computations. So it's very simple to run. So and within 5 or 6 steps, you're going to reach the optimal value. Okay, so that's more or less what we use in econometrics. So even with simple models like the logistic regression, you still need optimization routines to estimate parameters. Okay, it's not usually what we do because this is the simplistic way to do econometrics, which is maximize the log likelihood. But usually in econometrics, we have something more. It's not only about accuracy, it's also about simplicity. So we have this parsimony principle, which is we want a good model, which is going to be as accurate as possible with the highest log likelihood, but also it should be as simple as possible. It's related to Occam's razor, saying that if you have the choice between 2 models giving you the same kind of accuracy, go for the most simple one. Okay, so it's something we want to integrate in the model. We want something simple because we have the feeling that if the model is simple, it's going to generalize well. This property is how we frame things in econometrics. It's framed differently in machine learning. And again, I hope I will have time to get back on that. It's related to this idea of cross-validation in machine learning. But usually in econometrics, we really want to solve this very first equation. We want to minimize the accuracy, so the log likelihood. So minimize minus the log likelihood, and we put a penalty. Okay, so it's always penalizing for a complicated model. So the sparse model is the one when you have a lot of covariates in your model. Unfortunately, this equation is extremely difficult to solve, just because of this non-convex problem, because we add those indicators, so it will give you non-continuity. So this first problem is complicated, but it's possible to solve much more simple models. The one you have in the second is the ridge regression. Ridge regression has been introduced in the 70s by Arthur Earl. And actually, when you look back at the papers where we explain why he introduced this problem, actually his point was just, so he was a statistician and econometrician, but as I told you, you need a computer to solve your maximum likelihood problem. And using a computer in the 70s was taking time and money. So he wanted to make something very simple to avoid problems of being able to invert matrices. So he had this little term on the right, which was add the sum of the square of the parameters. This is the ridge regression. And it's extremely interesting because it's very related to what people do in machine learning, which is related to the fact that it's going to give you a biased estimator, but this estimator can have a very small variance. So it's something that people look more and more in machine learning, which is the fact that maybe looking only for unbiased estimator is not a good idea, which is still what people in econometrics like to do. And then I will talk a little bit about lasso. So lasso is more or less the same problem, except that you don't take the square of the parameters, you take the absolute values. So this is still continuous. You lose a little bit the differentiability because the absolute value is not differentiable. You have this problem in zeros where you have the, but it's still possible to get a subgradient, so it's still possible to do things. But this problem is more interesting because actually it will give you sparsity. So it's going to be used to make viable selections. Okay, so this is my L2 penalty. So this is the ridge regression. So we have this minimization of maximization of the log likelihood, which is the minimization of minus the log likelihood. And I have this penalty. And interestingly, if you get back to your courses in econometrics, adding a penalty is like writing a Lagrangian, which is solving a constraint optimization problem. So we still want to minimize minus log likelihood under the assumption that the sum of the square of the beta is not too large. And because we have the sum of the squares, it means that the beta should be in a circle. This is the equation of a circle or a disk. It should be within a disk. So you want to find the optimal value given that you belong to this red area. So it should be a disk. And what we can do is actually play on the lambda and see what's happening. So what we can see is that we have this kind of property. So we're going to shrink. Actually, we have this idea of shrinkage. We're going to get a smaller beta. So this will be a bias estimator because we're no longer on the optimal value, but it's a parameter that will have usually a smaller variance actually. Okay, so we're going to get a trade-off between the bias and the variance. And we got, interestingly, we got first an explicit solution for this one in the context of regression. And there is a Bayesian interpretation of that one. Okay, so it's like adding a prior basically on your parameters. And when you want to do this for a lasso, so in that case you get the absolute value. So you're not on a circle, you're on a box. Okay, but again you want to solve the same kind of problem. You want to find the minimization of your convex function, the blue one, under the assumption that you belong to the square, the red area. And what you can see is if it's too costly to get parameters, then you're going to get this shrinkage. Okay. And interestingly, when you look at it precisely, you always end up on the border of the squares when you're no longer in the maximum of the likelihood. And what it means basically is that you're going to end in corners of the box, and being on the corners of box means basically you're doing some variable selections. You're going to set precisely some variables at 0. So you're going to make some variable selections actually. Okay, so that's what we do. So there's a lot of connections between econometrics and machine learning and optimization at least. And something I want to stress is the fact that least squares is machine learning. If you want to get more, you need assumptions on the distributions. But I think it's way too simple because actually when you get back to what we do as econometricians, we want to solve these equations. basically we ask the computer to solve this equation, and assuming that y conditional on x is a Bernoulli variable with this probability, I think it's a story we tell ourselves, because actually you can solve this equation even if y is not equal to 0 and 1. You can still run a logistic regression when y is equal to 0.2. If you've been working a little bit on claims reserving in actuarial science, you know that it's possible to run a Poisson regression even if the y observations are not integers. You can run a Poisson regression even only if you have positive variables, which is kind of weird because you cannot have 1.3 claims. It has to be an integer to have a Poisson model. So I think this idea of assuming that you have a probabilistic model is somehow a story we tell ourselves as econometricians. And it has a lot to do with what Ariel Rubinstein was writing in his paper, or in his book on fables in economics, which is the fact that as economists, we like to tell stories. Economic models, it's like a fable. We try to tell a story about the data, and then we try to find the math that fits with this story. But again, it's possible to get the same math without the story, actually. So we have to be a little bit careful. Now, if I get back to my classification problem, I told you it's possible to get the same thing with a different approach, which is exactly this idea of Fisher. Fisher says something very different, which is I don't want to focus on y, I'm going to focus on x. If I assume that the x in the two classes, the red and the blue, will be Gaussian distributions, if I'm going to use a Bayesian formula to invert it and to get the conditional distribution of y conditional on x, well, you end up with a linear separation that will be given by this kind of expression, which is exactly a logistic regression. Okay, so if you assume that you have this Gaussian assumption on the x, which is more or less what we got on the left of the slide, we assume that the points of a Gaussian distribution, which is not very realistic here because, well, obviously we're on the square, so it cannot be a Gaussian distribution, but still, if we assume that we got Gaussian distributions, then we can estimate the line that is going to separate the red and the blue points, and actually we can get probabilities to be red or to be blue in any part of the square. And the outcome is actually a linear model, and it's very close to the logistic regression. The only difference is on the way we estimate the parameters. Because for the logistic regression, what we did was maximum likelihood. Here we have exactly the same structure for the model, except that we're going to use estimation of the Gaussian distribution. So we're going to use the estimation of the averages and variances of the x to get the beta. So once you understand that, basically you understand everything that we do with machine learning, which is always come up with the same kind of model, except on the way we estimate quantities that we need. Okay, like support vector machine. So this is an old technique coming from machine learning. Super vector machine is something like that. So we have to start with something very simple, which is what if we got points, red and blue points, and it's possible to separate them with a line. So it's possible to put a line and to make sure that all the red points are above and all the blue points are below. Okay, and obviously there will be thousands, millions of lines, so you want to find the best one. The idea of SVM is to get the line that will be the most far away from the closest point. Okay, so you want to minimize these to solve this problem, which is try to find the maximum of the distance between the closest points. So it's a maximum of the minimum. So it's a max-min problem. And in that case, you want to solve this problem. So I'm not going to spend time on that. You want to minimize this problem. But in many cases, it's not separable. You got a mix of blue and red points. So you need to put what we call a soft margin, which is had a cost for being wrong. And interestingly, when you want to solve it, you end up with solving a linear problem, and you end up with a model that gives you a straight line. But again, because it's a machine learning problem, we don't have any probabilistic interpretation. So I don't have my model. But interestingly, 26 years ago, Platt said, okay, I'm going to put a distance. So I'm going to quantify the distance between the point and the line, and I will interpret that as probability. So what it is, when you read the paper, is going to fit a sigmoid function after the supervector machine estimation. So what it suggested is to take this sigmoid function out of the model, and he ended with a logistic regression, basically. So if you run a plain SVM and you ask for a prediction with this Platt extrapolation of ex post probabilities, somehow you end up with a logistic regression again, but estimated differently. Okay, this is more or less what you got. What about neural network? So before going to neural network, first I will get back on logistic regression. So this is the logistic regression. We got the inputs, the nodes that will be the entries, so the variable you use in the model. The outcome will be the y, and you're going to put weights. So my beta will be the weight, and then I have what we call the we have this sigmoid function, which is basically a logistic function, and this is the outcome of a logistic regression, which is actually a neural network without any layers. Okay, so keep in mind that actually logistic regression is not far away from the neural network, because if you consider a neural network, you get something like that. So it's not a deep neural network. I got only 2 layers. Okay, so I'm going to assume that between the first variables we observe and the outcome, we create some fake variables. Okay, so we want to optimize it. Okay, so we're going to do some sort of feature engineering. So the only difference with feature engineering is basically in feature engineering, you start with your variables, you're going to play with them. So you're going to regroup them, you're going to mix them, and then you're going to say, okay, now I created some variable, I'm going to put them in a model. And this is what we get here. Okay, so at the end, what you get is a logistic regression, but not on the initial variable. You get logistic regression on the last layer. Okay, so on your feature engineering. So if you do some feature engineering on your covariates and then use a logistic regression on the new variables, well, somehow you get a neural network. The only difference with classical feed-forward neural networks is basically you optimize the creation of the layers. Okay, so it's not going to be ex ante feature engineering, it's more ex post optimization of the layers we created. But again, the ending structure of the outcome is a logistic regression. It's the sigmoid of a linear combination of some covariates, or transformation of linear transformation of the covariates. So all the models converge to this idea of using a logistic regression. So if I want to get something which is not close to a logistic regression, we need to go a bit far away. This will be trees. So trees is a way to get something very different. So again, I'm not going to spend too much time on that, but this is the outcome of a tree. Okay, so trees is about cutting the region of the X with straight lines, and then it sequentially to get those regions. Okay, so it's possible to get something very different. This is coming mainly from computer science. Okay, so it's really about this idea of cutting things properly, but it has probabilistic foundations, because when you end up, so first the way you split is based on statistical properties, and then you end up by taking averages of different quantities. Okay, so just to show you the differences between all the different kinds of models, I'm going to show you some machine learning, I'm going to show you some econometric models. So I created some fake data. Okay, so I've been using something that looks like a linear model, a logistic regression, but I added a nonlinear component. Okay, so this is exactly my scatter plot. I got my surface of probabilities, and on the right you get the level curves of the probabilities. Okay, so it's not far away from the linear model, except on the borders where we have something slightly different. Okay, so this is how I generated my models. How I generated my data. Now I'm going to fit different models. So I start with logistic regression, very simple. I got my straight lines. All those problems are going to give you straight lines, because that's how logistic regression is working. It's about getting an exponential of linear combinations. So whatever the way you estimate your quantities, so either pure logistic regression with maximum likelihood or with some sort of penalty, you always end up with the same kind of model. So this kind of having a penalty is going to shrink the parameters, but at the end you end up with the same kind of model. So the way you design the model, it will be the same. The only thing that is going to change is how you estimate those quantities. Again, it's possible to get variable selection with lasso, because some variables will be equal to 0. This is my linear discriminant analysis on the top left. Again, it's more or less like the logistic regression. And then I can get something which looks like a tree when actually we don't use the variables, we cut them, which is what some models have been using. I mean, I think about emblem that was used by pricing actuaries a long time ago, which was don't take any continuous variable, just cut them. So actually, if you cut your continuous variable and put them in a logistic regression, you end up with what you have on the left, which is rectangles. Okay, so your areas will be rectangles, which is more or less what you can get with trees. Okay, so trees is a way to optimize the way you cut your X space and say, okay, in this area, I'm going to predict 0.4, and in this one, it will be 0.83. Okay, and then we can do something a little bit more exotic. So SVM is more or less a logistic regression because of the Platt transform at the end. But again, it was designed without any probabilistic framework, but then we can get a prediction. And then we get something which start to be more interesting, which is mixing different models, which is the idea of ensemble methods coming mainly from machine learning. This is random forest. So the idea of random forest is actually I'm going to merge different trees. I'm going to create a lot of trees and I'm going to merge them. Okay, so you get something like that, which is extremely erratic. Okay, so you can get a lot of variability. Okay, so it's very complicated because you don't really understand what's going on. When you look on the top right, you can see that there are some blue points in a very red area. So it's going to give you very weird things. And this is what you got when you start to do what I call econometrics, but with non-parametric structure, which is add some nonlinear functions. And this is also something that actuaries have been using a lot because you want to use a model that you understand, which is a logistic regression, but you're not sure that the X1 should be put as it is in your model. You don't know if you should put the age in the linear model because, well, maybe there will be a nonlinear transformation of the age. The age influences the claims frequency, but maybe not in a linear way. So you're going to assume that you got a function and you're going to estimate it. Okay, so you can put some piecewise linear functions, or you can put some squares, some cube or whatever, but it's possible to get something very simple. And you will see that you get something extremely nice. So just if you want to understand where I am in terms of positioning in between econometrics and machine learning, clearly GAMs are very powerful techniques because you get the probabilistic structure of economics, but you also add a little something that is going to give you flexibility where you can get nonlinear transformations. Okay, so just to maybe conclude, I will talk a little bit about ensemble. So ensemble has to do with creating a lot of models and packing them. So we got parallel ensembles. We're going to get bagging. So we're going to create fake data, create different models and aggregate them. Or we're going to get the sequential approach, where we're going to get the boosting. So boosting is about learning and then getting errors, learning from the errors, and learning from the errors, and learning from the errors. This will be two different approaches. So this is bagging. So this is the bagging of the random forest. And as you can see on the right, you get the value on the diagonal. Okay, so the black line is the true probability I've been using to generate my data. And the curves you get are the one estimated by the models. So here it's not working mainly because by default, when you run a random forest on a classification problem, you don't end up with probabilities. You end up with something very weird, which is a majority vote. You want to know in how many cases you got ones. Okay, so it's not a probability per se per leaves. It's about getting the majority, the proportion of cases you got the majority out of all the trees you've been creating. This is what you got on this graph, right? So if you look at the evolution of the graph, it's not working well. You don't estimate properly the probability, the underlying probability. This is what you got with the regression. With regression, at least you capture something, but the price to pay is extremely high. You got a lot of variability, which is extremely problematic if you want to use random forest in a pricing model, because what it says is if you assume that X is the age, what you say is if you go from 21 to 22, you can move a lot. So your prediction at 21 can be 0.2, but at 22 will be 0.6, and so on. So you have a lot of variability that is extremely difficult to handle, actually. Okay, so this idea of trees is nice. You create a lot of trees and then you merge them. So you're going to get all the trees to predict on all the X. The other approach is about boosting. Boosting is start with a very simple model, which will be my red one. So everything is very flat. So I'm going to assume that everywhere you got almost 50%, except that I learn a little something. So what I learn is basically that on the top right, maybe you're a little bit blue. and on the lower corner, you're a little bit red. Okay, so I'm going to learn a little something, and then I'm going to get errors, and I'm going to create a second model, and a third one, and so on. So you keep learning. So it's what we call weak learning. You don't want a good model, except at each step you're going to get something that sequentially is going to learn. If you get back to econometrics, it's something you never do in econometrics, because basically when you run a classical regression, the residuals will be orthogonal to the x. So basically, once you run your regression, there's nothing you can learn from your residuals, unless you go outside of the linear models. But if you run a linear regression on the residuals, you get zeros. Okay, it's not the case with trees. So basically, if you run by very simple trees, you can see that you're going to learn sequentially. Okay, so you start with the red prediction, so everyone will be close to 50%, and then you start learning a little bit, and you see that you get this distortion and get closer to the true value. So this is boosting. Boosting is extremely nice, except that you need to stop at some point. And this is the tricky part, okay? You need to stop. You end up with something extremely complicated because you don't know exactly what, you don't have a model per se, you get predictions, okay? You get a sequence of trees, you can get thousands of, tens of thousands of trees as a model, but you don't know exactly what's going on, okay? So it's very difficult to interpret, okay? So I think I'm running out of time, so I'm going to maybe skip this part and mention, just take 2 minutes to, well, maybe I can skip also this part, except that I wanted to talk about something that we call calibration.
Maybe because it's very interesting, you can take perhaps a little more time after.
Okay, so I'm going to take 10 minutes.
I am not sure that on the basis of your presentation, we can have a very short discussion. Maybe we should plan to have something and to answer questions after people have reread your presentation, because it's really, really very, very rich and very, very stimulating.
Okay, sure. Okay, so thank you, Philip. So just to explain what was missing here. So I was talking about cross-validation and about the fact that this is exactly boosting. So we start with a model and we want to learn something. So how do we do as econometricians? Basically, we're just going to compute things. We're just going to do the math. If you get back to the way we estimate metaparameters, we always do the math. We're going to compute the biases, we're going to compute the variances, and we want to minimize the MSE, which is the sum of the square of the bias and the variance, and you try to get a formula. With machine learning, you don't care. You're just going to split the data in two. You're going to get a training sample and a validation sample. You train on the data set, you estimate on the second one. So basically, you don't do any math. So this is the main difference between the two. So I'm going to be fast again. If you have questions, I can get back on that. But I wanted to talk about scores, because I've been talking about predictions, but usually we care about the scores, mainly because, again, I'm going to get back in actuarial science. As actuaries, I don't care about predicting who's going to die. I care about getting a good estimation of the probability of dying, because I'm going to use that as my model, as my pricing, as a quantity that will be used in my pricing. So we need a good score, okay? We don't need a good prediction, we need a good score. And something you should keep in mind is the fact that when you run a logistic regression, you get this score. This is the exponential of the linear combinations. Interestingly, if you take the square of this quantity, you still get a score. And actually, you can use the square of this quantity to make your predictions. Because if you want to classify, you just say, okay, if I'm higher enough, then I'm going to predict a 1. If I'm too small, I'm going to predict a 0. But you can do the same on the square of this output. Except that this quantity has a very precise interpretation. It is what we use in the probabilistic model to get the probability to get a 1 or to get the expected value. If this model gives you the expected value, it's perfect, because you can do that as an actuary to get your pricing. Okay, so we need a good score. So unfortunately, when you get back to econometrics, there's no clear explanation about what a score is. When you get back to this textbook by Gurriero and Jaziak, where it's about econometrics of individual risks, they have this statement that actually all the information is summarized into this score. Okay, so they call that the canonical score, but there's nothing about the fact that this score can be actually interpreted as a true probability to get a 1. So this is what I wanted to conclude with, which is, can we get an interpretation, a probabilistic interpretation of that score? Okay, so first I want to emphasize that what we want to estimate is the expected value of y conditional on x. This is the regression function. Okay, so this is what I will call mu later on. I'm going to use the model S, and I want to know if S can be used as a proxy for mu. That's more or less the question we're asking. So something that was interesting was the property of balance that we got with the logistic regression. Property of balance says that if you got a score, a predicted score S hat, it's a good score in the way that it's going to provide you this global balance in the sense that the expected value of y is equal to the expected value of S hat. What you pay is what you collect. The average value of the losses is equal to the average value of the premium. Okay, so this is a nice property. This is a balance property. Again, if you use a logistic regression, you end up with this kind of property, which is desirable. And unfortunately, we cannot get that with machine learning, but we get that with regression. Now, can we go a bit further? We want this property to be valid also perhaps marginally. So if I focus on some x's, can we still have the balance? Actually, it's possible if the x is categorical. If you get back to the minimization of the maximization of the log likelihood, the first order condition, if you differentiate with respect to a categorical variable, you end up with the same property. If you got males and females, what you end up with is the fact that if you look only at males, the sum of the prediction is equal to the sum of the observed values. So it's also valid per subgroup if you use a logistic regression. That's nice, but still we're not yet to the calibration problem. Actually, we get calibration if we get this property not conditional on x, but conditional on the score. So what it says is basically I'm going to take all the values that were predicted at 0.4. So I'm going to take all the people that were predicted like 40% chance of dying, and I want to make sure that what we observe is equal to what we predict. And that's nice because not only it has a probabilistic interpretation, but also some sort of epistemologic interpretation, because it gives you an interpretation of what the score is. If you say that S gives you 0.4, and if the average value of the Y is equal to this 0.4, what it says is basically that the 0.4 is the average value, the average number of people that are going to get a 1. So what it says is S hat as a probabilistic interpretation, so it's related to the underlying probability to claim a loss or to die. Okay, so it's a way to define a probabilistic interpretation in terms of scores. It's actually the definition that you can find for the weather forecast in the UK. They wrote a lot of articles in the 60s say that when they say that you got 40% chance to get rain today, what it says is, well, first, the interpretation is complicated because if you got 0, if you got 1, there's no way to say if the model was correct or not. Okay. So if it's a one-shot probability, defining one-shot probabilities is difficult because usually probabilities are based on the law of large number. Okay, so to say that the probability is 40%, you need to repeat the experiment a lot of time and then you end up with 40%. But for one-shot event, there's no way to say if 40% was correct. The only way is to say, okay, I'm going to collect all the days we predicted 40% chance of rains, and then in 40% of those days, there should have been rain, which is exactly this definition of calibration, right? So we want the expected value of y conditional on the prediction to be equal to the prediction, okay? So this is exactly the calibration curve. And unfortunately, so it's not well studied in machine learning, and a lot of models in machine learning don't satisfy this property. The other thing is, when you look at the probabilities of the scores, which is what you get on the top of the bottom right, the distributions of scores are very different, which is kind of weird because so maybe I can go to the application I got. This is motor insurance. So I got a portfolio with people claiming a loss in motor insurance. So this is very real data. Okay, and I'm going to look at people claiming a loss. Okay, so I test different models. So on average, they are okay. Something like 8.7% of the people claim a loss within the year. But what we can observe is the distributions of the predictions are very different. This is the prediction on the left you got with econometric models. On the right, you got machine learning. Okay, so on the left, you got the GLM, you got the logistic regression. Then I got a GAM because I got the age, I got the power of the car, I got different continuous variables, and I don't want to put them linearly in the model. And then I got my boosting and I got random forest. And when you look at it, you get very weird outcomes. For instance, if you look at the table, you can see that for 10% of the prediction with the random forest, you end up with values smaller than 0.0006. So basically what it says is it makes a lot of sense to ask a premium which is less than 60 euros if you got an average loss which is close to 1,000. Okay, so it's not very realistic. Okay, a lot of people will be charged a very small amount of money. A lot of people will be charged a lot of money. So we have a very deep, complex problem when I start talking about machine learning, which is what do we assume about the underlying probability of claiming a loss? Should it be extremely diverse and very spread on the unit interval? Should we have a lot of people with absolutely no chance to claim a loss? Or should we get something like we used to have with logistic regression, which is more or less people between 3% and 50% chance to claim a loss? Again, it's very difficult to say anything. The thing is, when you look at calibration curves, so calibration curves, it's about the fact that I'm going to look at the prediction. So I'm going to look, for instance, at people that were predicted 7% chance to claim a loss. And I'm going to count how many people got a claim and who got predicted 7% chance to claim a loss. And actually with GLMs, you got something well calibrated because all people predicted 7% chance. The proportion of people claiming a loss was between 6 and 8%. If you take a random forest, you can be very, very far away. So we have problems with machine learning because they give you something which has a lot of very good properties in terms of accuracy, which could be seen as interesting in many cases. But if your point is to get calibration, which I think actuaries need this property, then you end up with a problem because we have absolutely no guarantees about calibration when you focus on machine learning because we don't have deep roots in terms of probabilistic models with machine learning, but we have them with econometric models. So it's possible to say something. And I've been playing with different models. So I've been playing on generating data based on regression outcomes with machine learning outcomes, and we end up with very weird results, especially with the random forest. So random forest is extremely nice. As you can see, sorry, I'm a bit fast on this one, but it's a very good model in terms of accuracy, but that's it. If you move away from accuracy, it has absolutely no property at all. The distribution of predictions is very weird. Properties in terms of calibrations are very poor. So we have to be extremely careful as actuaries when we start moving away from econometric to machine learning, because actually we're going to lose a lot of statistical guarantees we got when we were using probabilistic models. Okay, so I'm going to wrap and leave you some take-home messages, which is the fact that econometric models are interesting because of the probabilistic properties. Okay, except that I focus only on one case, which is the fact that we have tabular data. Okay, so it's usually the data you have in an Excel sheet. You got your variables as columns, but if you got pictures, if you got text, then possibly it would be more complicated. The other thing is machine learning is not very good when you don't have, if you miss a little bit about the structure. So if you have time series, it's more complicated to use machine learning. You need some very well-designed like neural networks that take into account the dynamics, but machine learning is based for individual observations. When you have time series, well, as econometricians, we know how to deal with them. Okay, so we have very different perspectives in machine learning and econometrics. The thing is, there were extremely interesting tools in terms of computing coming from machine learning. A lot of algorithmic advances that can be used by econometricians to get more advanced models. And again, it's possible also to do the other way around. Maybe it's possible to use probabilistic models into machine learning to give more structure and to quantify uncertainty. There's a lack of interpretability in machine learning, but I think that the good thing about those discussions about interpretability in machine learning is that actually it highlights the fact that the way we're looking at interpretability in econometrics was way too simple. The classical ceteris paribus approach in econometrics was very wrong, especially when you start to have big data with a lot of proxies, a lot of correlation. We miss a lot of things about the interpretation. So it helps a lot to understand econometric models. So in a way, machine learning is challenging econometrics. And I think it's a good way to move forward. And I think we should get more and more discussions between the two communities because, again, as econometricians and actuaries, we love to have probabilistic foundations, but there are a lot of interesting ideas coming from machine learning that can be used in this area. So I'm going to stop here and leave some room for discussion. And again, if I don't have time to answer, then well, you got my email and you can ask them, and I can give you some feedback.
Okay, thank you so much, Arthur. It's a very, very, very stimulating presentation. Of course, we are going out of your presentation maybe with more questions than solutions, and
Yes.
with probably more to do than done. Effectively, what is very, very interesting is that, of course, we were quite all aware that machine learning is rising problem of interpretability, but what you have pointed is that beyond this question, there are more profound questions which are addressed to econometrics as well as to machine learning. And therefore, as your conclusions say, we should try to blend both, but it's really demanding, and not only in terms of data, but also probably in terms of work to be done. So thank you so much. I very much appreciated this presentation, and at the same time I am going out of this presentation with more doubt on all my econometric and statistical work, which is a good thing.
Yeah, I got to admit, I mean, I'm a professor, I'm not a consultant, so I'm not selling you solutions, I'm just bringing you our problems. I'm here to think and to leave
a
open
good
questions.
thing, because you say, okay, there are solutions which are just apparent solution, comfortable apparent solution, but of course you have not solved your problem, and it's one of the reasons why also with econometrics at the end of the game we are always surprised why, with time going on, econometrics could be so unstable. Is because we are not addressed the true question of probability, at least not solve it. But sorry, I am not the competent guy, and I have to confess with humility that I listened to you and just was thinking how to do such kind of work. And I will leave the floor to the Q&A, hoping there are some questions, but maybe people are more to think about than to ask about. Please, you have the floor. Raise the hand for those who want to ask a question, and don't hesitate. It's not, I will say, you are probably all much more competent than myself, and you see, I have been, even myself, I have been able to raise some comments, and therefore you should be much better at that than myself. Please, don't hesitate. I don't see hand raised. I have no question to my knowledge in the conversation. Okay, I think here I will stop before asking question. Maybe just one. You say it's a hope in your last comment, blending econometric rigor with is there with machine learning's flexible function approximation. Do you think it's something which you say it's a promising path forward, but it is something we could be able to do without spending too much time, too much IT modeling, etc., etc. Is it something really realistic at this point in time to bet on?
Well, it's a difficult question. I think everyone is moving into this direction, saying that well, the thing is yes, machine learning has a lot of flexibility because it's possible to deal with different kind of data. So it's possible to get pictures, to get text. It's going to wrap up things to create feature engineering, and then we can get back to original econometric models somehow. So it's possible to do the two together, or maybe sequentially. You use the power of machine learning to deal with something you cannot deal with econometric models, and then you try to wrap up everything with econometric model because it gives you more confidence. But
Yes, it's a
it's too
two-step
complicated.
process. In fact, you are proposing. There is a question which is in the similar of Nicolas Guéry. Maybe Nicolas, you could just take the floor and ask your question. Otherwise, of course, I can read it, but the best is perhaps you take the floor, if you agree.
Sure. So thanks, Arthur, for this very rich expose. No, I was wondering if you were aware of a case in the actuarial industry where the two approaches would be blend together, the econometrics and the machine learning. Is it already done or not? And if yes, in which cases?
I think it's inherently done in many cases because I think for years now people in machine learning understood that it was not enough, that they needed more confidence interval and stuff like that. So they started to take parts and blocks from econometrics to put them into the machine learning framework to get confidence interval and do some tests. I think it was also the case for econometricians that were using like cross-validation to get better outcomes. But I think my point was more about the fact that like if you got text or if you want to do some claims reserving based on reports or based on stuff like that. Indeed, in the industry, I've seen some people working on reading text, extracting information, put that together in an Excel file or in a document that can be used as tabular data, and then get back to classical econometric model because they want to get more confidence in what they do. So I think it's something that is done, especially dealing with text and dealing with pictures. When you start to use satellite pictures to see something, you want to get scores, like was there a change in the evolution of the fire, evolution of the river level or something like that. You create a model to get something that will be used in future engineering. So maybe you can do this part, create some. So feature engineering can be done with machine learning very clearly because it's very good to deal with pictures and text. But at the end, I think it's like the neural network. At the end, you want to wrap up everything with an econometric model. That's mainly what I've seen in the industry.
Okay.
Do you think, Arthur, that also currently the use of course, information, for example, on newspapers, some kind of word or situation that are gathered together in order to get an idea, for example, of geopolitical risk, which is, of course, much more linked firstly to text than to data, and then after applying econometrics is, of course, going in that direction.
I'm not and I don't know exactly in this kind of risks what people are using, but when I was thinking about causal inference. For instance, causal inference is a very hot topic in econometrics. Econometricians have been working on that problem for decades, and I think they designed the good probabilistic way of looking at the data, saying that some people were targeted with a treatment, you got this propensity score. So I think they got the good design of the way things are working. And then you got papers like double machine learning, where basically you keep the model you got from econometrics, and because you got a lot of quantities, you can estimate them using machine learning. So it's possible to keep the structure that you got with the propensity score, with weighting based on propensity score, but compute propensity score using machine learning, using random forest. So this is more or less what Sonata is doing. In causal trees, is use the econometric model with plugging machine learning. So it's something also very common to use the power of econometrics to get structure and then use machine learning. I mean, we've been working a bit on that in the context of modeling decisions of agents. Like, we want to understand how people are playing lotteries. So you got a lot of experiments in economics where you assume that people have some sort of utility function and stuff like that. So you got the pure econometric model, and then you got neural networks. And what colleagues have seen is basically if you do both of them at the same time, neural networks are not performing very well. But when you start to put structure in the neural network, saying that agents might have a utility that will be increasing and convex, then it helps a lot the model. So this idea of flexible function is extremely important. But you need some structure. If you don't put any structure, it's going to learn anything. It's going to be very stupid. So I think we need the structure that we have from econometrics because it was designed for economics, because we have the economic modeling. We assume that we have a theory behind, then we want to estimate parameters, and this is very robust. But if you go out of the blue and try to get something, usually it's not that good. I mean, sometimes you get lucky and you say, oh, it's performing extremely well, but it's just luck most of the time. And I think this is where we are like for generative AI. We end up with something, in some cases it sounds outstanding, but in some cases it's just pure hallucination. You don't know why, and you're stuck. And if you don't have any confidence, I think it's not that good. So I didn't mention any generative AI, but it's also something that could be interesting. It's possible to make connections. I have some slide at the end where I try to talk about generating data, because in econometrics and machine learning, we try to create some fake data. But most of the time when you look at the way people create fake data in econometrics and natural science, they use behind a logistic regression. So you put a little bit of nonlinearities across the appearances, but it's very simple. And it's possible to use outcomes of machine learning, like random forest, that will be very weird, and see how it's performing. And what I show at the end of my slide is basically econometrics models behave extremely well, even if you use a very weird generating process based on machine learning. So we have this robustness of econometrics, which is something extremely important, I think, for the industry and for actuaries. We need robustness, I guess.
Yes, I see your point. That is what you are saying is as just reversing what we sometimes hear, that is use first machine learning so that you extract some correlations on some relationships, and thereafter use econometrics in order to be sure is not pure affibulation. But in fact, what you on your side recommending is to do quite the opposite. In fact, because you are not sure that machine learning is the good first step, because it can tell any story, a lot of stories, which most of them could be just totally wrong.
I'm also saying that sometimes it could be interesting to challenge.
Yes.
If you get an outcome and if a machine learning gives you something very different, then question yourself. Possibly machine learning was not correct, but at least question yourself and look. And most of the case is because you missed something in your model.
Yeah.
So we've seen that a lot, and it's exactly your point at the beginning, which is you just run a logistic regression, you get poor results. You run another one, you get much better results, and then you say, okay, now I need to understand why. Maybe I missed some nonlinearities, maybe I missed some correlations.
Exactly.
So I try to catch up then, and this is exactly what we did 10 years ago in the paper with Antoine, which is actually when you try to challenge the model to improve your econometric model, at the end, you end up with a GAM model, which is as good as the one you get in machine learning. And to go further in the story, when I was running my pricing game a long time ago, the winners were always people working with GAMs. So do a little bit of engineering, do properly your econometric model, try to understand the structure, but at the end, use an econometric model. And it was always performing extremely well, even in competition.
Okay. Just, because we are now out of time, quasi out. Let me just look, Arthur, if there are further questions, please. Are there further questions? Or last question one, knowing that if needed, you can ask questions directly to Arthur, or using or addressing them to us, the employee and myself, or even to look at the SCOR Foundation website. I don't see further hand raised. Therefore, Arthur, I should thank you very, very, very much. It's a very, very good presentation, very stimulating, one of the most stimulating, unfortunately, because we have to work on it and think about it. But thank you so much. And your presentation was also very clear, very pedagogical, and therefore it's a very brilliant presentation. Thank you so much, Arthur, and we hope to see you next. And in any case, we remain in tight relationship.
Exactly. I'm not very far away.
I hope you were not standing up too soon in the morning.
It's okay. I usually wake up at 5. It's okay.
About 5. Okay. Thank you so much, and I apologize.
Thank you very much, Arthur,
Thank you,
for
everyone.
the webinar.
Bye.
Thank you,
Bye-bye.
everyone. Bye-bye.
And thank you to everyone. Bye-bye.